Hi everyone, today we're going to learn another powerful uh, algorithm design technique, namely backtracking algorithm. Backtracking is a general algorithm for finding some or all solutions to complex problems, such as N-Queen's problem, in which backtracking algorithm explores all initial options to the solution, only recursively explores the, the promising options and abandons uh, all other non-promising options to avoid unnecessary checking of nodes until exhausting the rest of promising options in the state space tree. Let's see an example of n-queen problems. To start this n-queen game, we should at least we should have n by n checkboard, um, and once we have this n by n checkboard, we want to place one queen at each row. For example, here is one solution for this 4x4 n queen problem. For each row, we want to place one queen, and we do not want to place another queen on the same row. So for the second row, we also want to place one queen, and the same applies to the rest of the rows. And also there are some other rules applies to a good solution of n-queen problem. We show that no multiple queens can be on the same row. We also does not allow multiple queens on the same row, or multiple queens are placed on the same diagonal lines. So what does that mean is, let's say we have to make a decision if we can place a queen at this position, and we have to make sure that no other queens are placed at X position, no other queens are placed at the same row, no other queens can be placed on the same column, as well as be placed on the same diagonal line, both main diagonal line and also the diagonal line here. So let's think about the size of the n-queen problem. First, we consider the naive brute force approach to solve this problem. We can easily see that for a 4-queen problem, the problem size is 4 by 4 by 4 by 4, meaning it is n to the power of n, which gave us 256 candidate solutions, which is bad because it's more than exponential. It's worse than exponential complexity, time complexity, and we can try to show the candidate solution with a full state space tree, and the space tree will look like something similar to this one. As we can see, we start from the root, and for each node, the first number is the row number, the second number is the column number. We are only interested at the number of the leaf of this tree. So there are 256 candidate solutions at the leaf. So that's why it's not very good. And the question is, since we know use brute force is not a good approach to solve this anchoring problem, but can we use a better approach than checking 256 different candidates and to see if each of them is a good solution? The answer is yes, and we can use depth first backtracking algorithm to get reduced number of candidate solution. Therefore, we can save computational time. Let's see an example to solve 4-queen problems using backtrack. And first we we start at first row and first column. We place the queen at first row and first column, and then we're trying to see if we can place another queen on this board. We can, since we placed the queen on the first row, so we cannot place any more queens on the first row. So we start at second row, and we notice that we cannot put the second queen on the first column, nor I can place the second queen on the second column. The only place that I can place the queen is on the third column, second row. So we place that queen on that position, and we keep going, and we want to see if we can put the queen on the first column, third row. Apparently, it will tax on the first queen we just placed previously, and also we cannot put the the third queen on the second column because it would attack the second queen in diagonal line, and we find we cannot place the remaining position with this additional queen in the entire third row. So that becomes a dead end. So we want to say that we want to backtrack one step, and by going up one level, so the level above this dead end is the second row. So we want to explore if the next option of the second row is promising node. So we remove this queen, we erase the existing queen, and then we try to place the second queen on the last column, and we see that is a good position because it won't attack any other queens. And we keep doing the similar process, and we're trying to see if we can place another queen on the third row. The first position is not good position because it will attack the first queen, and we're trying to see if the second position is a good position. It seems is a good position because it does not attack any other queens we have previously placed. And then once we find this node is promising, we want to explore its children. So we want to go next one level. So we want to consider the last row, and we noticed we cannot place the queen on the first spot in the last row because it would attack the first queen. And for the rest of the row, we cannot place this queen to the rest of the row because they are all attacking one of the queens that we have previously placed. So in this case, we went to a dead end. So what we do is we backtrack one level and we removed that queen we have previously thought was promising. So we remove this queen and we want to place this queen to the next spot, which is here. But if and then we try to do it, but we find out that if we place this queen at next position, and it will attack the previous queen. So this position is called non-promising node. So we keep trying, and we want to see if the next position is a promising node. It turns out it also is not promising because it will fight with the previous queen that you have just placed. So in this case, we want to backtrack a level and we focus on the second queen we have placed, and we want to erase it. And once we erase it, this queen cannot go any further to the right. So in this case, we want to backtrack a level. We focus on the first queen on the first row, and we want to erase it, and we want to put the queen on the second spot on the first row. Then we are going to do the same thing to check any of its children is promising. We find out the last spot is the node that is promising. Then we keep exploring to the next level of the row, and we found out that the first position is a promising because it does not attack with any other queens. Then we keep exploring to explore all its children, and we're gonna check if we're gonna place a new queen on the last row. So the first position is not a good position because it will attack the previous queen you have just placed, and the second row is not is not a promising position because it will attack the previous queen in diagonal line. And the third position actually is a good position because it will not attack any other queens. So that's the whole process of solving one 4x4 4 queens problem, and we can use this pruned space tree to show the process of pruning the non-promising node and keep exploring any promising node. So in the end, we can see the shaded node is the promising node. So once we found uh, once we find that node is promising node, we can call this solution is a good solution, as we show the uh, the solution here as a good solution for 4 queens problem. So uh, so we know the process of solving n queens problem. So we can also look at it pseudocode of n queen backtrack algorithm. And first we need to have a base case in case that we are checking, after we are checking all the elements on the last row of the checkboard, we want to return true, meaning we have already arrived a good solution. If that's not the case, then we want to create a loop and trying to see if every node on the first row is promising. If it's promising, then you can place a queen on that spot, and then we want to explore if all of its children are promising by recursive calling this n queen backtrack function. If any of its children are promising, then return true. If none of its children are promising, then you remove the queen that you have placed previously. Then you end this loop, and the last step is return false. So that is the pseudocode for n queen backtrack function. So you may wonder why we need to study backtracking algorithm. Backtracking algorithm is more efficient because it abandons each non-promising options in searching for solution. Therefore, backtracking performs better than exhaustive search, also known as brute force. So let's trying to analyze the time complexity of naive brute force for n queen problem. Actually, the problem is on the order of O of n power of n, because in the space tree it has n to the n's leaves, so it's worse than exponential. So if we consider a by 8 n queen problem, then it will give us more than 6 million candidate solution. And if we consider the time complexity of backtracking n queen algorithm, we can consider its upper bound, meaning that no queens, we consider situation that no queens can be placed in the same row, so we can calculate the upper bound by summing up all the nodes in the state space tree. So if then we can substitute the number 8 into this formula, and and at the end we can the result is a little more than 0.1 million candidate solution. So if we take for 8 queen problem, if we take the number of operation using backtrack divide by number of operation um, we need to use by brute force algorithm, the ratio is less than 1%, meaning the backtrack algorithm is very efficient compare with brute force approach.